part of class. So now we're going to have a closer look at integrals. So integrals, how did they came into being? Well, we have looked at derivatives and that kind of stuff. And if you remember all the way back at the beginning of the semester, well, mathematicians didn't like it when we couldn't go back, so that if there was no inverse operation, remember exponential functions? Well, you could take the inverse of that by just taking the logarithm of it. And such a thing happens for derivatives as well. So if we consider this, so there is some kind of path that we follow and we end up from our function to our derivative. And that happens to be this operation. Well, is there an operation we can do to go back? And as there turns out, yes, there is. It's an integral. Okay, and integrals, when we get to it, basically, and I think it's safe to kind of call it like this, they are anti-derivatives. And I'll talk a bit about that more as well, but basically it's a very limited definition of what an integral actually is, but that is a good way to start thinking about them if you've never considered them before. Okay, now that we have this, well, I kind of want to make sense of this because, well, most of the time everybody has learned in high school that an integral is a surface, right? It's a surface under some kind of graph. And let me kind of give you an explanation why that makes sense. And for this, I want to consider one function. I want to consider, and we're just going to look at it on the positive side, it just makes things easier. So I just chopped off all the other parts of the graph and we'll say x squared, and that's our function f of x. Well, we can go already that path down and we find that our function, our derivative of that is 2x, and we'll call that f prime of x. Okay, so how did we get there again? Okay, for this, let me kind of dig up again what the true definition was of a derivative, because it was not just that. Well, it was, we take the limit of some small movement that approaches 0, and we're interested in our movement then along our function, and we get that, and we derive that along, we divide that by a small movement along our x-axis. So kind of what you're doing is you're kind of taking an average of movement, right? Which just happened to be our directional coefficient, right? So here we found an expression for our directional coefficient. Now what everybody learned probably in high school is, well, all you need to do is find the surface underneath of that. And why does that make sense? Well, if we look at this, right? So this is f prime of x. Well, if we see this, we kind of want to go back to that. And if we kind of close our eyes a little bit, we can say, well, we can kind of do that if we say, well, these little delta values that we need to do, well, we can multiply this again times it. And of course, be very careful with what I'm saying here. There is still that limit. I'm not just allowed to do that, but it's just to give you some kind of intuition. So basically what you're doing here is you're doing some small movement on the x-axis times a function. And what do you see what you want to do? Well, this is going to give you a very general expression, but what you want to do is, well, you want to find it for everything. So basically what you're going to do is you're going to take the sum of these things. Okay, so, but what does this actually mean, right? So it means you have some kind of function value right over here, and you're going to say, okay, we're going to take that function value, we're going to take it for a small value of x, and we're going to do that times delta of x. And what do you see then? Actually, yes, you do end up with some kind of surface, right? And this is the way we can go back. Of course, be careful, this limit is still there, it's not a proper definition of what I'm saying, but we want to do that for all our points. And here we take another point, so that's another f prime point, so we'll call that 1, f prime 2, and we can go on, and then we take the same small step again, and we add those up together. And then you see, well, you can kind of revert back to it. Well, this happens to be, well, very interesting. Well, how do you go back? And you'll see that these things look very similar. It's just this symbol takes into account what I'm saying here, like you want to do that for every little part, and we have to be careful with that limit. Basically, the way we go back is we take the derivative of our original function x, and we're gonna integrate it over x, and this dx just means, remember, same thing as here, a very small steps of x. Okay, so this is kind of as a brief introduction for integrals. So this is also, well, this logic allows you to find actually a lot of anti-derivatives. So integrals, so the basic ones. So let's consider a couple before we really jump into the exercises. Imagine that I asked you, our function is x squared, let's derive that. Well, you find that that's 2x. how do you go back from this now? Really think about it. How could you go back from this? What happens here? Well, and what is a generalized way of doing this? Well, if we integrate 2x, well, how could we go from this to this? So that's actually the inverse operation. Well, what do we see is that we're going to say, instead of bringing down our exponent here and then doing -1 in our exponent, well, we're going to say we take our exponent and we do +1. So exponent is +1. But if we just had this doesn't match yet, because here we have x squared. If we were to derive that, we would get what would we in this case we get x squared. But that doesn't really make that much sense yet, right? Because, well, we have 2x and we want to go back to 2x, we want to go back to x squared, right? So here we need to be, well, careful. We still need, well, because, well, that 2 is still in front of it because, well, we didn't touch it. So what do we want to do? Well, maybe I can make it a bit clearer by moving the 2 just in front, because it's just a constant. We can do that. Basically, we still want to divide that 2 away. So basically what happens here, and that 2, where does that come from? It's just the 1 plus 1. Okay, let's consider that over here. Why does that make sense? Well, basically what you have here, you have a function that says, great, we have here x squared. If we derive that, what do? Let me write it down step by step. It means we bring down our exponent and we do x squared minus 1. So we want to think of the inverse of that. Well, first and foremost, what we're going to do, well, we want to divide away what happened over here, and then we want to do plus 1. So really see this as an antiderivative. So this part over here is basically going to tell you that, well, in the exponent you do plus 1, and then you need to derive away what the exponent was before. Okay, so this is kind of like the idea of an antiderivative. So basically what you want to do is, like, you have this thing here, try and derive it, and then think, well, how can I go back, right? And all of these basic derivatives, you can find an overview of that in the theory overview. These are, I encourage you, this is a good way to think about them, but study them, like really know them, because it will help you a lot. But most of the time, they're just the inverse of what you did for derivatives. So that means that, remember, the derivative of a sinus of x would yield you cosine of x. Great, so that means that the integral of cosine of x just goes back to what we had before. It would tell you that it's sinus of x. And for those who aren't paying attention, I have to be careful because there needs to be a plus c, right? Because information is lost when we derive, but I'll get back to that as well. And then the opposite for the derivative of the cosine of x, I'll let you think about that. So let me get a bit more into what these plus c's mean. Well, if we take a non-defined area and we just take, well, some kind of, well, entire function and we integrate it, well, remember when we were to derive it, how could we distinguish this function, the derivative of this function, from this function? Well, we couldn't, right? If we were to derive this, we would end up, this is 2x, and this is 2x as well. So that means that there is some kind of, well, it's still possible that we were dealing originally with another function. It's just by deriving we lose some information. So that's why we say when we work the way back, we can say we can approximate this f of x, but we only can get so close. We get some kind of function that's very similar to f of x. I'll put a little wavy part over the f of x plus some kind of constant, because that information was lost beyond repair. Okay, so getting back to all of this, of course there are techniques if you know a little bit more about this function to get this back, but this for now. Okay, so this is pretty much all about integrals. So first things first, we're going to do some basic integration technique exercise, and we're going to calculate a couple of definite integrals. And a definite integral, what does that tell us? It basically tells us when we have this, it tells us that we're interested in finding the area between 2 points. We'll call them A and B. How do we do that? Well, what you actually do is first you calculate the entire area of B. So you say the B area. But that was of course too much. So what do you take off? You take off the smaller area of A, and that would yield you the area between A and B. Okay, in between a and b, so I'll write it like this. Okay, so here we're not interested in finding a very general approach, we're actually finding like, oh, how great is this surface in between those 2 points? Okay, so let's have a look at that. So for this, we're going to start with exercise 1a. So let me wait a second while my computer is busy. So basically over here, we get the derivative between 1 and 3 of the function y squared minus 4. And we're interested in integrating that with respect to y. And this is actually why we start with this exercise, because I'm sure many of you who have already seen an integrals, you're so used to seeing x over here, but it doesn't need to be. We can calculate things in the opposite direction or functions with different variables as well. So here, you always have to be very careful to what this says, because this means that we're integrating into that. So in this case, I could give you a very complicated integral and all in function of x, and if I just write dy to it, well, then the answer is fairly straightforward, because this means that any other variable that's not y, we'll consider it as a constant for now. Okay, so we have this thing here over here. Well, what do we do? First things first, well, we're going to rewrite this integral a little bit. We'll say, well, this is the integral between 1 and 3, and let's expand this out. So we get here 1y to the power of 3 minus 4y, and again, all of this, we're interested in deriving that to dy. Why is this? Why did we do this? Because it's much easier as it was to derive polynomials. It's also much easier to integrate polynomials. Because what do we see? Well, we see that the integral of this is just y to the power of 3 plus 1 over 3 plus 1. Again, you can only do this for polynomials. And then well, the other thing we see, it is 4y, which was raised to the power of 1, plus 1 over 1 plus 1. And we're interested in calculating the area between two parts, so we can write it for now, and this is a very general way of doing it, as between 1 and 3. Okay, let's rewrite it a little bit so we have a little bit of a neater function to work with, and we get y to the power of 4 over 4 minus 4y squared over 2. And we're interested in calculating that between 3 and 1. Okay, so what do these 3 and 1 mean? Well, these 3 and 1 are basically our upper and lower bound. Remember, b and a. So what does it tell us? Well, it means if we follow this logic over here, you take the greater area, so the one that's further along the x-axis, and you subtract the smaller area in this case, and that's less far along the x-axis, you get the area in between them. So you always have to make very sure that this bound, let's call it a and b, well, no, let's not do it the other way around, so b and a, b always needs to be greater than a. If that's not the case, well, it means that you're calculating the inverse of it, right? So you're doing the opposite. What you're doing is you're getting the small area, you're subtracting the big area. Well, what do you get if you do this minus the big area? Well, you end up with, again, this size, but now the negative of it. So yes, you can flip these things, but then you have to be careful with the sign. We're going to make exercise on that in later exercise sessions. So what do we do now? Well, we're interested in evaluating this, and as it turns out, it's fairly straightforward now. If we were to evaluate that, we just have to fill these points in where we had our variables. So we had 3 to the power of 4 over 4 minus 4 times 3 squared over 2. So that is the area for our big triangle in this case. And then we subtract, well, one of our smaller triangles, so minus, and then do the same thing for 1, so we get 1 over 4 to the power of 4 minus 4 times 1 squared over 2. And this would actually be our area. And then I might hear you thinking, yeah, but Arne, you told us about these c values. Well, actually, what you can kind of imagine for definite integrals is that there is here also a plus c that we don't know. But if you were to fill that in, well, you get here plus c, these actually cancel each other out because you get plus c, negative c. So they always cancel each other out. So for Definite integrals, you can just forget about that c. But it doesn't disappear, it cancels out. Okay, now that we have this, well, we can just simply work this out. So here we get 3 to the power 4, so that means that's 81 over 4. Here that's 36 over 2. And here we get minus 1 over 4. And here, careful, minus and minus becomes plus, means 4 over 2, or in other words, plus 2. I'll just leave it as 4 over 2. So let's bring all our parts together. So we already know that we have here 81. So we get here, if we bring those two together, so we get here 80 over 4. And here you get 36 over 2 plus 4 over 2. So here you get minus 32 over 2. If we were to rewrite this now, we get that this is 16. Oh, sorry, what am I saying? This is 20 minus 16, or in other words, it's 4. So the area between 1 and 3 underneath this function, it is equal to 4. The inverse function, so the function we originally started with before we derived it, was this. So the integral allowed us to go back, but the area we're really interested in now is this part over here. It tells us it's going to be 4. Okay, let's make another exercise at this. So we go to B. And here, what do? We have here the integral of between 1 and 2 of x squared over x to the power 4, and then still minus 1. And again, we are integrating to x in this case. So this is probably more at home feeling, right? Because we're integrating into x. So in this case, again, what can we do? Well, we can always try, let's convert it back to a polynomial, but here we have to do it in such a way that it respects that, right? So in this case, what could we do? We say 2 and 1, we get x squared over x to the power of 4 minus 1 over x to the power of 4. And of course, all of that is still integrated to dx. We can rewrite it a little bit, and we find that that's between 1 and 2 of 1 over x squared minus 1 over x to the power of 4 dx. Or in other words, if we write a little bit, and you remember, I do the same with derivatives because it allows us very clearly to see what we're working with. This is x to the power of negative 2 minus x to the power of negative 4. And we're interested in integrating this. And great, we just have another polynomial again. So that means we can just say x to the power of negative 2 plus 1 over negative 2 plus 1 minus x to the power of negative 4 plus 1 over negative 4 plus 1. And all of that in between the 2 points we're interested in, which is 1 and 2. Let's rewrite it a little bit so it looks a little bit neater. So it is minus x for this part, so because this becomes just x, it just not just x, it becomes negative x, so it is minus 1 over x if you rewrite that. Okay, then for this part, well, what do we get? We get that that's minus x to the power of negative 3 over negative 3, so it becomes plus 1 over 3x to the power of 3. Just getting rid of those negative exponents and stuff between 2 and 1. Okay, let's fill that in. We start with our greatest one at first, minus 1 over 2, plus 1 over that 2 to the power of 3 is 8, so 3 times 8 is 24. Then minus our new area, so I'm going to write it as between big brackets. We get negative 1 plus 1 over 3. Okay, or in other words, we can rewrite it a little bit more. So here we get, this is negative 1, 24. We're going to put them all on common denominator. I think 24 is the closest one. So here it becomes 1 over 2 times 12. So negative 12 over 24 plus 1 over 24 plus 24 over 24. That's that 1. And then negative 3 becomes minus 8 over 24. Bringing all of that together, we end up that our area under that part is 5 over 24. Okay, so far for question B. Okay, then let's consider one more, and I think that's the final of the really basic ones I'm going to make together with you, but that are definite. The other ones, well, I hold back a bit on making those until you've seen the rest of the video, especially well, the second exercise. The third one you can wait a little bit for, and then you can calculate those areas as well. So between 8 and 1 of u to the power of 1 over 3 minus u to the power of minus 1 over 3, and all of that derived to u. Not derived, integrated. I'm going to make this mistake a couple of times. But of course we're integrating. So here again we're integrating to u, and we have again some kind of polynomial. So we can just do the following. In this case, well, we have u to the power 1 over 3 plus 1 over 1 over 3 plus 1 minus u over minus 1 over 3 plus 1 over minus 1 over 3 plus 1. And that evaluated between 1 and 8. Okay, great. This looks like a whole mess, so let's clean it up a little bit. So here we get it's u to the power of 4 over 3 over 4 over 3. If we change that a little bit, we get here that it's over 4, and then the 3 that was divided here, it moves up, so 3 times that, minus, let me give it a little bit room, and here the same thing, we get u to the power of 2 over 3, moving the 3 up, and keeping the 2 down between here, and then evaluated between 8 and 1. Okay, let's fill this in. So we get 3 times 8 to the power of 4, third power square root of that, over 4, minus, here again, 3 times 8 squared, third power square root, and of course these are numbers that you can use your calculator for. All of that is the surface of our furthest along the x-axis minus the one that's less along the x-axis, so it's 3 over 4 minus 3 over 2. Okay, after using your calculator, I hope you get the same result over here as I did, but here you get 48 over 4 minus 12 over 2 minus 3 over 4 plus 3 over 2, which gives you, if you calculate that, this becomes 6, and then here if we bring those together it becomes plus 3 over 4, so in other words it's 27 over 4. That's the area under that part of the integral underneath your function. So that's the integral of it evaluated between 1 and 8. Okay, all of that being said, let's move on to exercise number 2. And the goal in exercise number 2 is that you just make a couple of exercises and you really think about, well, applying those, well, basic integrals. So in that case, let's maybe make exercise D, because A, B, and no, let's start with C, because A and B are very similar to what we already did. So exercise C, let me get it here. So we find that we are interested in this kind of it's not a definite integral, and we're asked to evaluate it between 4x to the power of 3 minus 7x squared plus 2 over 3x minus 15 dx. Okay, and we're just evaluating it of a polynomial. So let's go through it. We say, okay, that's 4x to the power of 4 minus 7x to the power of 3 over 3. And then we hit something. We hit the integral of 2 over 3 times 1 over x. Right? I just brought it out. And then you say minus 15x and all of that plus c, some kind of constant. Okay, so why didn't I just do the same rule over here? And then I want you to think about it. Well, yes, x squared, if we derive that, well, what do we get? If we derive it, so d over dx, we get that that's 2x, right? But what would it make look like 1 over x? Or if you say 1 over x squared, if you were to derive 1 over x, what would you end up with? Well, again, here you actually have x minus 1, so you would drop it. So you would, if we have to derive that, it would become minus 1 x to the power of negative 2. So yes, this just follows those polynomial rules, right? Because going back, all you need to do is add it up and then get rid of all the exponent that you would end up otherwise. Well, what derivative gives us 1 over x? And well, if you remember correctly, the derivative of ln x is the one that gives us 1 over x. So if you see 1 over x, it means that you're dealing with an antiderivative of ln x, so an integral of that. So let's clean this up while I go through it one more time. X over 4 minus 7 over 3 x to the power of 3 plus, this is an ln, 2 over 3 ln x minus 15x plus c. So really be careful. Yes, if you can split everything up as a polynomial, that's really great, but 1 over x, it's a tricky one. Don't get fooled by it, it's an ln, right? Because it was the same for derivatives. Okay, so why is this so neat? And what have we been doing in all the other ones? What do they share in common? Is that we can kind of separate them, right? We can separate them with a negative or a plus in between them. That's really great. And those are things we're gonna use later on as well. So really try to remember that an integral of a sum, so the integral of x plus x squared plus x to the power of 3 dx, it's much, much easier than if I wrote x times some other function, plus, yeah, maybe let's say here plus cosinus of x times x squared. This is a much easier thing because we can just split it up and chop it up and actually say we're just finding the integral of x plus the integral of cosinus of x plus the integral of x to the power of 3. So we can just chop them up. But for multiplication, we cannot do that. So then we need more clever techniques. So, but as long as we can chop them up with a negative or a positive sign in between them, we're all good. Okay, so that's for question C. Then let's do D. And here, we get here the integral of 2 to the power of x times 3 to the power of 2x times 5 to the power of 3x, and that derived to x. And here we run into the problem I was just talking about. Well, we cannot simply chop them up. We cannot say the integral times the integral times the integral, because here you're integrating. What you're doing here is you're just adding surfaces together, which is fine. But here you're multiplying surfaces, and that doesn't necessarily give you the same answer as you would have over here. If you were to say, okay, that's great, but I'm just gonna imagine you get some kind of function like this, and you say, well, I'm just gonna first take that part, then add that part to it, and then add that part to it, and it's gonna be exactly the same. Yeah, that's true. But multiplying all of these parts is not gonna give you the same answer. So we're not allowed to, we cannot split it. So we have to be a bit cleverer about this. So, but what can we recognize is that, well, we can work out these things. And why would we do that? Because, well, it allows us to see something. Well, we get here 2 to the power of x times 9 to the power of x times 5 to the power of x. Sorry, not 5 to the power of x, 25 to the power of x. Sorry, again, not true, 125 to the power of x, because it was to the power of 3. And all of that integrated to the x. Why is this interesting now? Because, well, we can reduce it now to a single integral. Because 2 times 9 times 125 raised to the power of x is the same as this. If that doesn't make sense, why it did it, well, it's a trick I think we applied also for logarithms. Well, think about it in this way. Well, we say 2 to the power of 3 times 3 to the power of 3. What's actually written here? Well, you can say that is 2 times 2 times 2 times 3 times 3 times 3. And what's great about this is that each of these 2's, because, well, there's the same amount, has a buddy here in 3, right? This one has this buddy and this one has this buddy. So If we were to multiply first, because of course multiplication is just associative, we can move it around, we get 6 times 6 times 6. Or in other words, we find that this is equal to 6 to the power of 3. So that's the same trick I used over here. Okay, now let's really consider, well, what the antiderivative of this was. Well, and maybe let me immediately solve this over here. We get 2250 to the power of x dx. Well, what would we need to derive to end up with this point? Well, as we see, well, with these exponential functions, well, often they repeat themselves. So this thing, if we were to derive it, yeah, this would be in there. But what would be the problem? Imagine that, let's do that one. So imagine we have y is equal to 2250 raised to the power of x. Okay, let's derive that. So we get, first we'll move it around a little bit using our ln. So we get ln y is equal to x times ln 2250, and I think some other people already noticed where I'm going at. If we now derive it, we find that that's y dy dx, and that's equal to 1 times ln 2250. So our derivative, in this case dy dx, is equal to the ln of 2250 times 2250 raised to the power of x. Okay, great. So this is what we would get if we were just going this way. But that was clearly not what we were integrating, right? So, well, what's wrong with that? Well, basically we see that we are ending up with ln of 2250 times too much. So if we want to say, well, we want to get rid of that, well, what can we do? We can say, let's divide it away, 2250. And then, yes, indeed, we end up with what we had here, right? So that means that this was not our original function. The original function we were dealing with was this divided by the ln of 2250. And all of that plus c plus some constant. Okay, let's do one more. And we'll do exercise F. And here we get that that's the integral of 3 minus the square root of 1 minus x squared over the square root of 1 minus x squared. Okay, so great. We can split this up a little bit, right? There's a negative sign in between of them, so let's see if we split them up, of course, using the proper fraction rules. So we say 3 over 1 minus x squared, and this becomes minus the square root of 1 minus x squared over the square root of 1 minus x squared. Okay, this is great. This allows us to see something already. Well, actually what was written here, we're interested in finding the integral of 3, 1 minus x squared minus 1 dx. Okay, we can separate this, so we can say actually what we're interested in finding is the integral of this over here, 1 minus x squared minus the integral of 1, and then of course dx on both sides. If I forget that dx, it means if you don't see it, it's not because it disappeared, it means that I forgot to write it. Okay, so now that we have these two things, well, we can easily see that, well, what function would we need to derive to end up with this? Well, we would need to derive the function x. But this one over here, let's give it one more try. So we say 3 times 1 over 1 minus x squared dx minus x. And then I cannot forget my square root over here. Well, for those who really studied their derivatives, they should recognize, well, this looks very much like a derivative of something we know, and yes, it actually is. And for this, if you don't immediately see it, you can go look up in the list. It's a bit more contrived where this comes from. This is 3 times the arc sinus of x minus x from here. And then we still have to add plus c. So here there was a plus c as well. So this is how the way we would solve of f. So really try these all at home. Try to make yourself familiar with them. It's fine if you go up and you say, well, I don't remember or I don't know yet what these basic derivatives are. Just look up higher in the function and try to use them to, well, uncover what it is. And then use that in further problems. Okay, then let's move on to the last series because I think you guys have had enough of this today. And here we're going to use one of our first methods. It's the substitution method. And I've given a quick overview in the theory. And I say, well, you tend to use that when you get something along the lines like this, where you have a function of some, well, a composite function, where this, well, the first function, this gx, can be found elsewhere in the function. So the derivative of that can be found. This thing over here. So when you have something like this, and I know this looks very, very complicated at first, but really, basically what you're trying to do is you're gonna try and find a function, something in the larger function, so the function within the function, that if you were to derive it, you would be able to cancel this part out. Okay, and let's make an example on it, and I hope that makes it clear. So we're gonna make question A. And we're interested in solving the integral of 1 plus x squared, all of that to the power of 1 over 2 times x dx. Okay, so what's different to what we did before? Well, it's not easy to split this up. It's not easy to bring this x in, and you would always be stuck with that square root. But here is where the substitution method becomes handy. The substitution method, it tells just, let's try and find a function where if we derive it, we end up with actually what we had over here, or something very similar. So in this case, let's say this is gx. And let's maybe not call it gx, but typically what happens is we say u is equal to 1 plus x squared. If you are not convinced why I'm doing this, don't worry. Follow along with the example, and I hope that it makes it clear what's happening. So if you say this, well, what is neat now is like, well, we can derive it. So basically we say, well, we say this is going to be u now, but then we want to be able to, well, no, we are no longer, that's no longer our variable. Well, our variable is now u, so we need to derive the derived variable. So we need to convert this dx. So what's the trick for this? We say, well, du, well, that's a weird u, du over dx, which is just the derivative of u, would be 2x. Agreed? So how could we, well, express dx? Well, if we say that means that du is equal to 2x times dx, bringing x to the other side, or in other words, it means that du over 2x is equal to dx. And now we're going to bring all of that together. And I hope that makes it clear. So what do we say is, well, we found here that this is u to the power of 1 over 2 by just saying this is equal to u. That's all we did. And then we're interested, and then we have times x, but that's really messy because we don't want to keep that x over here when we're deriving, because u is already a function of x. So this is a compound of x's. So we want to be able to cancel that out. We want to be able to scratch it out. So what we do is we say, well, now dx, let's substitute that also in, because we're no longer deriving to that as a variable. We're saying that that is equal to du over 2x. And luckily, this happens to just be what we were interested in. We can say this x and this x, they cancel each other out. So in other words, what do we have here? Well, we have a function, just 1 to the power of 1 over u to the power of 1 over 2 times du. And we are no longer dealing with any pesky x's ruining our integral. So what can we do now? Well, this is just a polynomial. We can just say u to the power of 1 over 2 plus 1 over 1 over 2 plus 1 plus c. We can rewrite it even a bit more. So we get here 3 over 2, and here we get 2 over 3 plus c. But there's one thing first, because, well, we're dealing with an integral in terms of x. We want to know our solution in terms of x as well. So we just substitute our x's back in. So we say, well, u was equal to 1 plus x squared keeping that power 3 over 2 over 3 plus c. So this is really what I mean when you're doing a substitution. You're really looking for something that you can cancel out, something that appears elsewhere in the function. You want to be able to scratch out all of your x's. If you make a substitution and you still end up with some x's or the original variable, it means that it wasn't the right substitution. And really make all the exercises. There are only 9 of them, but really make them, because especially substitution is it's the one that requires the most intuition to see what kind of substitution you need to do. That being said, let's make 2 exercises more together. So e is equal to the integral of e to the power of x times the cotangents of e to the power of x. And we're going to derive that. And again, this multiplication doesn't allow us to split it up, so we have to be cleverer. So let's rewrite it, because the cotangents, well, that makes me think, well, maybe we can use those cosinus and sinus. So we know that that's cosinus e to the power of x over sine e to the power of x dx. So now what's neat? Well, actually, you see is sinus e to the power of x, that has a very interesting property, because if you derive sinus e to the power of x, well, you should know that that's cosinus e to the power of x, so that would neatly cancel that out. But not would it be only cosinus e to the power of x, it will also be using the chain rule times ex, and that's that part over here. So what do I mean with this? I mean that u is equal to sinus e to the power of x, and if we derive that, we end up with what we can substitute. So we get du over dx is equal to cosinus e to the power of x times ex. Or in other words, this thing means that dx is equal to du over cosinus e to the power of x times e to the power of x. Substituting that back in, well, what does that tell us? Well, it tells us the following. It tells us that this becomes e to the power of x times cosinus of x, because, well, we didn't change it, e to the power of x, we didn't change that, over u times du over cosinus e to the power of x times e to the power of x. Now we can scratch out a couple of things. And again, we are dealing with an integral where we just have 1 over u du, which we know 1 over u, that's the one I told you earlier about. Be careful about it. It is ln u plus c. Substituting everything back in, it tells us that it's ln of the sinus of e to the power of x plus c. Okay, so this was the one before last exercise we're going to make. The other exercise I'll make it in a different video. It's again a substitution. We're going to make exercise I together. Okay, see you there. Bye-bye.